And welcome back. Alright, so last thing we talked about was Newton's second law. Before we go to Newton's third law, I want to talk about friction with you. So think about this question. Or this question. There it is. So why does a skateboard slow to a stop after I stop pushing it? Why doesn't it just keep going on in the same velocity in the same direction forever? We know it slows down. I'm asking you to think about what can make it slow down. Well, if it slows down, that's acceleration. Okay, it's negative acceleration. That's still acceleration. It's just going slower. It's changing its velocity. Force causes acceleration. So if the skateboard is slowing down, there is a force acting on it. What is the name of that force? What force slows down the skateboard? You probably already figured it out from the title of this thing. It's friction. And here's a definition of friction. Force that opposes the motion of two touching objects. I don't know if y'all can hear that or not. I have the window open for a breeze. And I think there's a cow out across the street making loud noises. Anyways, go ahead and write that down. Pause if you need to and come back to me. Welcome back. Alright, so please note, if two objects are not touching, there's no friction. You gotta touch for friction to happen. I really hope y'all can't hear that. I'm gonna try to ignore it as much as I can. Alright, do not write this down. Just read it and understand it. All surfaces are a little rough. All surfaces are a little rough. Even a baby's bottom still has some micro bumps. Micro bumps. Oh, you can ignore the page 71. That's an old text reference. I just haven't taken it out yet. One of these years I'll do that. So the bigger the micro bumps, the less smooth the surface, the rougher it is, the more the friction. Alright. You've read it. You've heard me talk about it. You've paused if you needed to. Let's move on. There are four types of friction: static, sliding, rolling, and air resistance, also known as fluid friction. I'm going to go over static friction first. Static friction is defined as the friction that tries to prevent two stationary touching objects from starting to move past each other. Pause, write it down, come back. Okay, stationary means not moving. So it's like when you're sitting at the top of a slide before you give yourself a little push. Why aren't you sliding down already? Static friction. That was easy enough. This is the strongest of the frictions of the four we're talking about. Sliding friction is the next thing. If you look at the picture I drew, the stick figure is going down the slide. Of course, stick figures don't wear pants, so it probably hurts. The definition of sliding friction is friction that slows down two touching objects while they are sliding past each other. If you overcome sliding friction, you can accelerate across a surface. Okay, you've paused, you've written it down. Let's move on. Rolling friction is a special kind of friction. It's the form of static friction between a surface and the part of a spinning wheel touching it. Bicycle, motorcycle, car, tricycle, I don't know, whatever else you drive, four-wheeler, six-wheeler, unicycle. I don't know what you have at home. I don't want to know. Alright. If you overcome rolling friction, you get what you call a spin out. Maybe you call it a burnout. I don't know. Depends on what you do in the parking lots. And also, if you have a slick road, like covered in ice or something like that, it's very easy to overcome the rolling friction because there's less friction there. So it doesn't take much force to overcome it, and you skid. The last kind of friction is air resistance, also known as fluid friction. It's friction caused by colliding with the molecules in the air. Alright, pause, write it down, come back. Alright, you're back. Let me get a sip of coffee. You paused, I didn't, so there we go. Alright, so I want to give you an example you've probably lived through. You take your hand, you stick it out the window, or your parents are driving you, or whoever's driving you, drive you down the road. You feel the air resistance. In fact, you probably do a whole, hand up, hand down, hand up, hand down thing. It's fun. Until they go too fast and they break your elbow off. No, just kidding, that doesn't happen. But you also know that the slower they go, the less likely it is that you're going to feel anything, the less fun it is. And if a bug hits you while you're doing that, well, that hurts, because it's going very fast relative to you. Okay, so you've had enough time to write it down, blah, blah, here we go. Air resistance causes this strange little thing called terminal velocity, which I need you to understand. So, how does air resistance cause terminal velocity? Pause, write down the definition. The fastest speed an object will fall. Okay, got it? Alright. Let me explain to you. Read with me. Two forces act on a falling object. Gravity pulling down and air resistance pushing up. As an object increases its speed through the air, the force of air resistance increases. At some point, those two forces are equal to each other. At some speed, those two forces become equal. Gravity pulling down and air resistance pushing up. Whatever's falling stops accelerating. It doesn't stop falling. It simply keeps that same speed until it hits the ground. Make sense? For an ant, that's a very slow speed. You can throw an ant from way up high and it'll survive the fall because it has a very low terminal velocity and its body can take the impact. You and I have very high terminal velocities. We can't take the impact. We would need something to slow us down, a parachute. What does a parachute do? It increases your surface area, increasing your air resistance and decreasing your terminal velocity to a speed you can actually handle. You still need to be trained on how to land. I still know a professional parachutist that can still break a leg or pop a kneecap out if they land just wrong. Gotta be careful. But at least it is survivable with a parachute. Alright. Now, you're going to be drawing some stuff. There's 4 spaces across the bottom. A, B, C, and D. They got little letters in them. There's a top box and a bottom box for each one. So you're going to draw the following diagrams in the top boxes. Put each picture in the properly labeled box. When done, write the descriptions of each from the slides that follow. There's the pictures. Pause. Draw. And then come back. Pause. And you're back. Okay. Hopefully you drew them all. Yeah, here we go. At time A, so underneath A, write this. The object has just been dropped. The only force acting on it is gravity. It isn't falling yet. It's like right when you boop, let go. Right there, that moment in time, freezing time. It hasn't fallen yet. It's just let go. Gravity is the only force acting on it. Nothing's holding up anymore. But it hasn't fallen yet, so there's no air resistance yet. So write down what's there. Right over there. Hey, pointing the right way this time. Time B. It's now picked up some downwards velocity, so now there is some air resistance pushing it up. The up arrow is the air resistance, the down arrow is the gravity. You might want to label those down arrows gravity, or grav for short, and the up arrows air resistance, or AR, if that helps you. So the air resistance is less than the gravity, which means it's not falling that fast yet. Alright, if you need more time, pause. If not, here we go. At time C, velocity has increased and so has air resistance pushing back up, but the two arrows are not the same length yet, so we're not at terminal velocity yet. We're still having a net force down, and so we're still having some acceleration. At time D, the force of air resistance equals the force of gravity, and the object does not fall any faster. It's still falling. It's still falling. Just doesn't get any faster. Whatever speed that is, that's the speed it keeps forever. Well, until it hits the ground, whichever comes first. That's all the notes for today. Congratulations. See you tomorrow.